In today's lesson, we're going to take an introduction to statistics, and specifically, we're going to talk about what statistics is, what are the important concepts that we're going to be looking at throughout the term, and sort of what's the foundation that we want to build on for this course. Really, my main goal with today's lesson is to try to explain why we care about statistics, sort of demonstrate that statistics is all around us, and provide us with a common vocabulary in order to be able to talk about statistics throughout this course. So it's going to be the introduction of a lot of terms, a lot of concepts just being introduced here. And so with that, we can get into today's lesson, where we're talking about primarily populations, samples, and processes. So in today's lecture, we want to define what statistics is and talk about why we care. We want to talk about the components of statistical inference. We're going to talk about how data can be categorized, the different roles for statistics, and the different types of statistical studies. So it's quite a few different concepts being introduced, but then throughout the term, we'll sort of dive more deeply into each of these. So it's this very high-level overview today. And to begin, I want to start with sort of the central question of today's lecture, and that's what is statistics and why should you care? And so that's what we're going to endeavor to answer. But to provide sort of a brief summary, there's a bunch of stuff on the screen right here that statistics is central to, right? And so you can start to peek into any aspect of life that you may care about. So maybe you're a sports fan, or maybe you've been following technology lately and you're quite familiar with the ongoing AI revolution that we're in. Maybe you're really into board games or poker or other card games or video games. You might care about politics. You might be really interested in engineering improvement. Maybe, you follow financial markets. Understanding any of these concepts, any of these topics, any of these areas requires a foundational grasp on statistics. At its core, statistics is about reasoning about uncertainty that we face, and generally speaking, every area that we're dealing with in life is going to have uncertainty in it. And so really, the tools that we're going to be talking about throughout this course are going to provide you with a new way of approaching problems, a new way about thinking through problems, any time that you might be faced with randomness, right? And so we'll touch on some of these examples throughout the course a little bit more, but I just really do want to underscore that statistics, especially nowadays with sort of the increasing availability of data that we have, is central to just about every avenue of life. And there's just about no topic that you can't take a statistical view of. And so I hope that given the broadness of that allows you to grab onto some examples that feel really familiar to you throughout the course and use those to propel your understanding forward. So to have a concrete example with us throughout the term or throughout the lecture today, what if we wanted to answer the question, does pay discrimination exist? Do women get paid less than men, for instance? Right? So how might we be able to go about answering that question? And this is the type of question that statistics can be useful for in terms of answering. If you start to try to come up with some ideas about how we might answer that question, there's several avenues you might take. So maybe what you're going to do is survey every single person in the world and ask them what their wages are, and then look at the discrepancies. And of course, we can't do this, right? It's not feasible to ask every single person in the world what their wages are. It's not even clear how you would go about thinking to do that. And even if you're working with a smaller population, say everyone in New Brunswick, you're still not going to be able to ask every single person what their wages are. And, people's wages are changing on a day-to-day basis. Maybe someone loses their job or gets a new job, right? So asking everyone, that's sort of out of the question. Right? So maybe what we do instead is we go to a single company and we see if there appears to be discrimination at that company. And this might work, right? You could do a full audit over all of the wages at the University of New Brunswick, for instance, but that's not going to tell you whether wage discrimination actually exists. That's going to tell you, does it exist at the University of New Brunswick, right? And so again, we're not actually sort of getting to the problem that we want to answer here. We could, say, take a look at internet data on salary websites, right? There are websites out there that people can go and post what their salaries are and make that publicly available, right? And so we could look at this data. And again, we're not going to really have an issue or a clear answer to the question through this. And the issue this time is a little bit less obvious, perhaps. But the types of people who are going to be posting their salaries onto public websites are not going to be representative of everyone, right? If you think about who leaves reviews on websites, it's going to be people who are, happy with the product that they ordered, or who are deeply unhappy with the product that they ordered. And it's going to be a similar situation on salary websites, right? It's likely going to be people who are either comfortable sharing their salary, so probably skews higher than average, or people who have issues with the company, and so maybe will be sort of pulled down. Either way, it's not going to be a reliable sample of the salaries across the population. And so sort of none of these strategies are going to work to answer the question, does pay discrimination exist? They're never going to give us accurate information about the problem as a whole. And so the idea with statistics is that we want to find ways of answering these types of questions, about getting an accurate picture of the population as a whole, when we really cannot get access to it directly. So, sort of in a lot of words, statistics is the process through which data are collected and analyzed in order to derive useful insight regarding a population or a process of interest. We're interested in the total pay and how that breaks down by different factors, right? And so that's sort of the population or the process that we're interested in. And what we want to do is collect data and then analyze those data in such a way that we can sort of gain useful insight, that we can generalize to the whole population. And everything that we do in statistics is going to sort of fall into this bucket here. Now, to define some of those terms in that definition, when we're talking about data, we're just talking about some collection of facts, right? So you might think about a spreadsheet of numbers as being data, but you could also think about someone's, textual response, right? Customer reviews on a web form, or an interview with someone, or a video, or pictures, right? And especially as, we progress through sort of the modern tech landscape, the data that's being generated now is largely multimedia, right? There's lots of videos being posted. There's lots of pictures being posted. There's lots of updates being posted. And all of this is going to be useful data for us. And so we say that data is, as broad as can be, a collection of facts. Variables are characteristics which are able to vary between different individuals, processes, or objects, right? So it's all of the different features that we might care about that are going to be different person to person. So we wouldn't really consider a variable as something that's going to be constant across a whole population, right? And so if you're just looking at students at UNB, you're probably not going to collect information about what university they currently are at, but maybe you would collect information about what high school they went to, for instance, right? Because that's going to differ between the individuals, but the present university that they're at's not going to. An observation is any single piece of data. So oftentimes we're going to make an observation about an individual, right, if we're dealing with people. Or maybe we're looking at manufacturing processes, so our observations are going to be samples off of the manufacturing line, right? Any sort of single row in our data, any single piece of our data is going to be considered an observation. And the idea is that we're going to take many observations to try to build up sort of a larger data set and use that to infer information about our population. Data are able to be both univariate, where we're just looking at a single piece of information for each of the observations, or they could be multivariate, right? So if you just want to know sort of the distribution of ages in this class, then we could just collect the age from every student, right? And that's going to be a univariate piece of data. Multivariate data contains multiple different variables, right? So maybe we take, individuals' height and their weight and their age and the high school that they went to and whatever else we could care about. That's going to be multivariate. Now, throughout this lesson so far, we've talked about populations, and I think we all have sort of an intuitive idea of what a population is. But in statistics, we're dealing with sort of this concrete notion. And so with a population, we want to have a well-defined collection of objects of interest, right? And so what we're saying is that a population is going to be, say, all people in the world who meet a certain set of criteria, all undergraduate students at the University of New Brunswick, or all professors in Canada, right? It could also be less defined about people, right? So if you're in manufacturing, you might have a collection of objects that you're producing using a certain manufacturing process, right? And so then all of the objects that are being produced according to that manufacturing process are considered a population as well. In a census, which again, you're probably familiar with the Government of Canada census, but the census is when you collect information on all members from a population, right? So you enumerate every single person that's in that population, and then you collect all of their information that you could care about, right? Generally speaking, censuses are not going to be feasible. And so instead, we typically look at a sample. And all a sample is a subset of the population, right? So we have a population as sort of the overarching group of objects that we care about. A census would happen if we could look at every single one of them. Normally, we can't do that, and so instead we settle for a sample, which is just going to be some smaller subset of this population. So we can think about this visually as we want to. And so right here we have this grid of colored squares, right? And we could think about this as being the full population here, right? So in this case, we can see every different square. Each of them has sort of a different color. So we can think about that as being the color being the variable for each observation. We can think about it as being univariate because we're just thinking about them as having different colors, right? Maybe they represent different categories or whatever, right? And so if we look at the population like this and we go through and we sort of enumerate the color, blue, green, 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 and so forth, then that would be a census of this population. But instead, you could think about us grabbing just a random selection of these squares, right? And so if we do that, then over on the right-hand side here in the slides, we have a sample from this population, right? And of course, the sample is going to depend on which individuals, which observations ended up sort of being selected randomly, right? And so if you do this a bunch more times, you're going to end up with different samples each time. Right? And so you could think about generating many different samples from any given population, and each one is going to be subtly different. And so the trick in statistics, or really the central problem that we're trying to deal with, is how do we take information from one of these samples that we've taken and use it to generalize information about the population when we know that every time we take a sample, it's going to be a little bit different. Our samples are never going to perfectly align with the population. And sort of whenever we're running this sampling process, we're going to get different results, right? And so how do we sort of take all of this uncertainty and make sense of it and still get useful information? And that's the goal of everything that we're going to be trying to do throughout this course. We have a few more important definitions to go over. So we consider parameters to be descriptive measures for populations. And generally, we're going to be interested in parameters. So maybe we think about the average height of a population, or the average age of a population, or the quality of product that's being produced, right? And whenever we're thinking about a parameter, this is some true value that really exists in the population. And what we want to know is what's the information about this, right? So back to our example from the beginning of the lesson today, we could think about the parameter as being the difference that men versus women make in the workforce, right? A statistic is a descriptive measure from a sample, right? So if we grab a set of people and we ask them their wages and we take sort of the average difference between these two groups, then that would be a statistic. So we have a parameter which corresponds to some measure in a population, and a statistic which corresponds to some measure for the sample. And so the idea with statistics is we're using statistics to infer information about parameters. So in statistics, if we want to sort of boil down what the process is, we're going to collect observations, and these are going to be observations of different variables, and that's what makes up the data that we have. Then we're going to use the data from some population of interest, and depending on whether we took all of the members or just a subset of the members, we're going to have either a census or a sample. And then our goal is to learn information about the parameter of interest using statistics that we can actually compute on our samples. And in this course, we're almost always going to be thinking about having a sample, not a census. Having a census sort of makes the process a lot easier, but it's also almost always infeasible. Now, when we're thinking about variables, there's several different types. And the reason that we care about the types of variables is because the way we're going to approach their statistics are going to differ, right? And so sort of the main breakdown is going to be categorical versus quantitative, right? So occupation might be a categorical variable, right? Where we're thinking about there's sort of different categories. You can enumerate all of the possibilities. And you would have years of experience, say, being a quantitative variable. There's actually sort of an associated numeric value to quantitative variables, right? So numbers correspond to quantitative variables, text, videos, images, that type of thing corresponds to categorical variables. We can also think about there being discrete versus continuous once we're thinking about quantitative variables, right? So if you're measuring your age in years, that could be a discrete variable, but your actual age is some, real valued number that's sort of a continuous variable. It can take any value along the real line, and so that would be a continuous variable. Now, these breakdowns seem fairly straightforward on paper, right? You either have numbers or you don't, categorical versus quantitative. Then with discrete versus continuous, there's sometimes a little bit more of a gray area, but can you sort of enumerate all of the bins that the number could fall into? And if so, then it's discrete. And if not, then it's continuous. But what if I asked you about education? Is education a categorical or quantitative variable? And the idea with something like education is that it's going to depend. Right? It's going to depend on what did we record for education. It's going to depend on what are we interested in, right? If I say that education is categorical because I'm asking you, did you complete high school? Did you complete an undergrad? Did you complete graduate school? Right? Then that's sort of categories. But I might also ask you, how many years have you been in school? Right? Or you could think about measuring education through, say, your grade point average, which would also be a quantitative variable. And then if you list a letter grade, well, now suddenly we're into categorical variables again, right? And so there's sort of a lot of room for choice in how we categorize these different variables. And ultimately, it's going to come down to what's the analysis that we want to run, and that's going to depend on our variable types. There are 4 overarching roles that statistics can play. And we're going to focus mostly on the first 2, but I do think it's important to sort of give you a complete picture. And so very briefly, we can think about statistics as playing a descriptive role, or descriptive statistics. And what this is asking is what has happened. We're trying to summarize information that we already have. We're going to describe the past in some way. We can also think about inferential statistics. And this is the idea of using the data that we've collected to draw conclusions, right? So is this process a viable process? Does this medication work at reducing the symptoms of the disease? These types of questions. We can also think about predictive statistics, and this is becoming more and more relevant in modern times. But with predictive statistics, we're asking, based on what we've observed, what do we think is going to happen in the future, right? We're trying to make predictions about what the future holds. And then finally, we can have prescriptive statistics. And this is a question of what should be done, right? So if you're wondering about what's going to most improve a process that you're running in your business, well, then you want to sort of make a prescribed solution to it, right? If you're a doctor and you want to know what's the medicine that's going to best improve this patient, you're trying to make a prescription. And so prescription is subtly different from prediction, but we really don't have to focus too much on these. I just want to point out that while throughout this course, we're going to focus heavily on descriptive and inferential statistics, there's sort of a lot of other statistics that we won't have time to get to. But if you're interested in, there's lots of information out there on it. And I'd encourage you to sort of take a look at the other roles that stats can play. Now, most of the information that we're dealing with in statistics broadly is going to come from what we would call statistical studies. And there's sort of 2 broad categories of studies that we can think about. So we can either think about what are called observational studies, or we can have designed experiments. In an observational study, they occur whenever the data that we're looking at have not been directly manipulated by the researchers. So there's some process or there's some way of observing that we're not intervening on directly, but that give us data that we might care about. So maybe what we're doing is we're going in and just collecting health records that already exist, right? And so that would be observational because we're not intervening on that. If you're sitting outside and you're just watching cars go by on the road, that's observational because you've not intervened in this way, right? And if something's not an observational study, then we would call it a designed experiment or an actual experiment. And in this case, it requires researcher intervention. And typically, we're going to think about this as being randomized, and we're going to use this to compare populations and processes. Right. So in a designed experiment, you might think about researchers who want to test whether one medication is better than another. And so they recruit a group of people, they give half of them the new medication, half of them the old medication, and then they see how does this differ. And so you've used randomization, you've actually intervened, you're sort of controlling what everyone's exposed to. This is different than the case where you go out and collect the health records and you look at them together. And the important difference comes in how we can use these to draw conclusions. So in observational studies, it's harder to determine whether we have causation, right? It's harder to know, did the medicine that some people take actually make them better? Or was that sort of observed because of other factors, right? Now, often you're going to see people say that you cannot make causal conclusions from observational studies. I'm pretty sure that the textbook that we're using in this course says this. That's not entirely accurate. It is definitely harder to draw causal conclusions from observational studies, but if you're careful with what you're doing and you sort of approach it correctly, then you certainly can. Okay, and so I want to sort of make this clear. The common example to pull out is that we know that smoking causes lung cancer, but it would be really unethical to run a study where we give half of the people in the study cigarettes and we force them to smoke them, right? So we clearly have not determined that through randomized experiments. And so because of that, it sort of has to be the case that observational studies can allow us to draw causal conclusions. And it's more advanced than what we're going to be looking at in this course, but I just want to emphasize observational studies can indeed give us causal conclusions. The thing that we have to watch out for is confounding, right? And so the issue is that, let's say that we're just looking at a data set, right? And we just look at smokers versus non-smokers. And we notice, well, smokers end up with lung cancer more often. We cannot necessarily conclude that it's because they were smokers, because smokers might have other factors that influence their propensity to develop lung cancer, right? And so these are known as confounders. And the idea with an experiment is that by randomizing people, we're sort of eliminating the impact of confounders, right? If you take in 100 people and you make 50 of them smoke and you take the other 50 and you say don't smoke, then you're sort of balancing out anything else that might be influencing the outcome. When you're using observational data, that's not balanced out. And so that's why you need sort of more advanced methods. In general, whether we're dealing with an experiment or an observational study, we need our samples to be representative. And so the idea is that we want the people that we're drawing conclusions about to sort of somehow represent the population as a whole. Right? And so if we think back to that first example and we asked, why don't you want to use the data that you can find for free online? The issue with that is that it's not going to be representative of the whole population. Right? And so we want to find ways of making sure that we have representative data. In order to sort of get representative data, we can think about how do we go about drawing samples. Right? And so there's a few different ways that you could think about sampling from a population, and we're not going to focus too much on them, but I want to, again, give you sort of a flavor of what these might look like. So one way about sampling would be what we would call convenience sampling. And the idea with convenience sampling is that we're going to select the individuals who are available, right? So I might come into this class and I might survey the students in this class. And convenience sampling, it is convenient, hence the name, but of course, the members of this class are not going to be representative of the university as a whole, right? And so convenience sampling does not provide us with a representative sample. And so because of that, while there are reasons to use it in certain cases, it's not generally going to be considered a particularly good form of sampling. Instead, we might think about simple random sampling. And so in simple random sampling, any observation from the population is going to be equally likely to be included in our sample, right? And so if you think about when we had all of those squares and we were taking samples of different colored squares, that's going to be a simple random sample because each of those squares was equally likely to get selected into our sample. So in our university example, we could list every student who was at the university, and I could just grab the emails from a subset of those. It's going to be simple random sampling. We could also think about something like stratified random sampling. And so in stratified random sampling, we're going to do a bunch of simple random samples, except we're going to perform those in different groups. So maybe the study that I'm running, I want to know about sort of the different faculties at the school, right? And so instead of doing a simple random sample of the entire university, I go to each of the faculties and I perform a simple random sample within each faculty, and then I combine those into a sample. Right? And so you could, of course, come up with different sampling schemes. These are just some of the most common. And again, we're not going to focus too much on any of these except for simple random sampling throughout the course, but to give you a flavor of sort of what's out there in statistics. In designed experiments, as we were indicating before, the randomization is going to be used to help eliminate the confounding. And the other thing that we'll point out briefly with this is that it's normally focused on a very specific intervention. You can't make broad conclusions, but you could say, does this very specific medicine help with this specific disease, right? So it has to be super focused in your conclusions. Observational data might give us the ability to ask broader questions because there's sort of more of it there. You're not worrying about what you can intervene on, but then we have to address confounding sort of directly. Now, this whole lecture so far, we've been talking about statistics and some different concepts and sort of giving a flavoring of what that is. This course is on probability and statistics, right? And so a brief note on probability. Probability sort of represents the opposite process to statistics, right? So in statistics, we have some parameter of interest and we want to sort of understand that parameter by taking samples, right? And so we have our data and we want to infer about the population. In probability, we do the opposite. We assume something about the population, and then we ask, if you're going to take sampling events from this, what do we expect to happen, right? So you can sort of think about it if we're flipping a coin, say, right? With probability, we're going to say, we assume the coin has a 50% chance of landing on heads, 50% chance of landing on tails, and you could ask questions like, what's the probability that you get 10 heads in 20 flips of the coin, right? With statistics, you're not going to assume that the coin is equally weighted, and instead you're going to flip the coin 20 times, and you're going to count how many times did the heads come up, and then you're going to say, do we think that the coin was equally weighted, right? And so you can think about them as sort of doing the inverse process of one another. Probability is also important because it serves as sort of the language of statistics. And so we're going to dive really deep into probability, and then we're going to use all of those concepts that we pull out throughout the remainder of the term. So to try to summarize briefly what we talked about today, introduced a whole lot of concepts and sort of, giving a taster of all of them, and then we'll start diving more deeply into them in the coming lessons. But from a overview, statistics is the process where we use data to make inferences about a population when we've drawn that from a sample. Parameters represent measures in a population, and statistics represent the sample quantities of those same measures. Variables can be quantitative or categorical. Quantitative variables can be discrete or continuous. Statistics can be used to describe, infer, predict, or prescribe. We're going to be focusing on the first two. Studies in statistics are categorized as either being observational or experiments. And probability is the task of performing the opposite role of statistics. That's basically everything that I wanted to cover in today's lesson, and so I will see you in the next one.